Welcome back everyone to 11.4, the comparison test. In this video we only have just these two examples to go through, and then we should be all set. So let's get to it. Alright, so in this case we're going to try to apply the limit comparison test, and I need to figure out something to compare it to. And well, in the denominator I have this n squared plus 1, and I like to pretend that that plus 1's not there. Right, this n squared is going to be much bigger anyway, so forget about the plus 1 for the time being. And then in the numerator I have this, well, it's n to the 1/2. So with a little bit of cancellation, we could see that a good thing to maybe compare this to is 1 over n to the 3/2. So that's what's going to be my an, my sequence that I compare to. Bn is, of course, the sequence that I have, this root n over n squared plus 1. And I want to look at this ratio of an divided by bn as n goes to infinity and try to figure out, does this converge towards any finite number? Well, if you compare it to the right thing, the claim is hopefully it does. So now instead of dividing by this fraction, let's multiply by the reciprocal here. And we can see this n to the 3/2 times the square root of n. Well, that's the same thing as n to the 3/2 times n to the 1/2. And we add these exponents together, and that's going to give us an n squared in the denominator. Now in the numerator, we still have our n squared plus 1. So let's go ahead and distribute this n squared. And so we get 1 plus 1 over n squared. Now let n go to infinity, and this 1 over n squared is going to approach 0. So this overall limit is going to approach 1. Now 1 is a nice positive constant, so we found something that we can compare to. So, well, 1 over n to the 3/2 we know converges. Why does it converge? Well, that's the p-series test. And the p in our case is 3/2, and that's, of course, well, greater than 1. So that's why it converges. So therefore, by the limit comparison test, we know that our series must converge. So in our series is, of course, this square root of n over n squared plus 1. So we've determined that this thing converges. All right, now I have one for us. This last problem is definitely more complicated. So I'd like to spend the rest of the time on this problem right here. So maybe the first thought we had is, well, if we could get rid of this 3, then we could do a good comparison here. But this e to the negative n squared and this e to the negative n will not really communicate well together. So in fact, I want to get rid of the entire denominator. Okay? So I want to get rid of the entire denominator, and the way that I'm going to do this is by noting that 1 is going to be less than 3 plus e to the negative n. Why is this the case? Well, of course, 3 is bigger than 1, and e to the negative n is going to be greater than 0. So now if I do my cross dividing, right? So my cross dividing, this is going to give me 1 over 3 plus e to the negative n is less than, well, 1 over 1. And now both n and e to the negative n squared are positive, so let's go ahead and multiply through this our inequality here. And we can see that n e to the negative n squared is greater than our function. So my idea is that this thing on the right-hand side should converge, and therefore the smaller thing will converge, right? This will be the direct comparison test. Of course, these things are both positive, so we can apply the direct comparison test. So my claim is, okay, why will this thing converge? Well, we need to use the integral test. So you can see that this is kind of a combo problem here. We apply the direct comparison test and we apply the integral test. Okay, now I haven't shown this at all. So let's go ahead and show that this function right here satisfies the conditions of the integral test. So the first thing, it is continuous, right? Nice continuous function here. Actually, let me go ahead and use x's. So yes, x e to the negative x squared. This is continuous. You're not going to be dividing by 0 or anything like that. The next thing is that it's positive, right? X is positive, it's 1 and bigger, and e to the negative x squared is also positive. And then finally, decreasing. And unfortunately, this is one of these things that you can't really use our theorem or tricks in order to show that this is decreasing. And the problem is because x is an increasing function. So we need to use the derivative. So, okay, well, we can go ahead and take the derivative of this. We just need to apply the product rule. So the derivative of the first times the second plus the first times the derivative of the second. And now we need to do a little bit of factoring. So let's actually simplify first. So this is going to be negative 2x squared e to the negative x squared. And now we can see that both of our terms have this e to the negative x squared. And what's left over is 1 minus 2x squared. And now e to the negative x squared, this is positive, but 1 minus 2x squared is going to be negative, right? Because x is greater than 1 in this case. So a positive times a negative is going to be a negative. Okay, so then let's go ahead and look at the integral from 1 to infinity, right? We can now apply the integral test, so let's apply it. So the integral from 1 to infinity of x e to the negative x squared dx. And this should look like maybe one of these classic u substitutions. So let me first go ahead and solve the indefinite integral. So let me use my green pen here. So the indefinite integral x e to the negative x squared is going to be the integral, and so u equals negative x squared, du equals negative 2x dx. And we can see we have an x dx, so let's divide through by negative 2. This is going to be the integral of e to the u times du over negative 2. Okay, pull out a negative 1/2, and when I integrate e to the u, I get e to the u. And then let's substitute back in negative x squared everywhere we see a u. Okay, now we're set up to use our improper integral. So this is going to be the limit as t goes to infinity of the integral from 1 to t of x e to the negative x squared dx. And we now know how to integrate this thing. So when we integrate this, oops, sorry about that. When we integrate this, we get our negative 1/2 e to the negative x squared. Evaluate from 1 to t. Okay, so if I was to plug in t into this thing, everywhere I see a x, well, this is going to be, in fact, let me pull out this negative 1/2 here. I'll pull out a negative 1/2. Okay, e to the negative t squared minus e to the negative 1. Okay. Oh, and actually, in fact, let me make one more change here. Instead of this e to the negative t squared, let me go ahead and write this as 1 over e to the t squared, using the properties of exponents. Now, as t gets very large, we can clearly see now that this approaches 0. So we're going to have negative 1/2 times negative e to the negative 1. Well, that's the same thing as 1 over 2e. Okay, so now we can see that this integral converges. So again, by the integral test, we now know that our series converges. So because this bigger series converges, by the direct comparison test, well, the series that we started with, this n e to the negative n squared over 3 plus e to the negative n, must also converge. All right, and that should just about do it for us here. As you can see, this last one is a little bit of a doozy, but it's nice to be able to see how we can combo both the integral test and the comparison test into one problem. All right, I'll see you next time in 11.5.